Okay. Oh, just forgot. Okay. Just a minute. Just record it here also. How do I record it? Okay. So now, so when the origins of K and K prime coincide, so this is what I call T equal to T prime equal to 0. And now, uh, since V is parallel to X and X bar, we have Y equal to Y bar, Z equal to Z bar. And so the system has been reduced. I mean, the transformation can be written as something which is reduced to two variables, just X and T or X bar and T bar. And so I can write X is equal to X bar plus V T bar by square root of 1 minus V square. When I say V square, I mean V square by C square. And then T is equal to T bar plus T bar plus V into X bar divided by 1 minus V square. Okay, so this we did last time, right? So you remember that, so now here V is dimensionless because it is ratio of V by C and C is taken to be 1. Okay, and now what we now do is, I will just for uniformity's sake, I will just write these as x0 and x1. So I will write x1 is equal to x bar 1 plus V x bar 0, 1 minus V square. And this one. X0 is equal to x bar 0 plus V x bar 1 divided by 1 minus V square. Okay. And now what I can do is, let me now take a differential of dx bar. So I have dx1 is equal to dx bar 1 plus v dx bar 0 by 1 minus v square, and dx0 is equal to dx bar 0 plus dx bar 1 by 1 minus v square. Now I can just divide these two. So so now okay. So if suppose so basically it says that if I have two particles whose x coordinates are x1 and x1 plus dx1, and okay, sorry. So if suppose there is a particle which is moving in such a way that at x1, at x0, its position was x1, and at x0 plus dx0, the position was x1 plus dx1. Similarly, for the barred coordinates, then the velocity of the particle, which I will call the script v, to differentiate between capital V, which is the velocity of the frame, this v will be equal to dx1 by dx0. You're with me here? Is it okay?
Yeah.
Okay. And so I can now use these two and calculate this. And we have, this is equal to, I will have dx bar 1 plus v dx bar 0 divided by dx bar 0 plus v dx bar 1. And this is equal to, I will just take this one. Yeah, I will. What I will do is, okay, so I will just take out dx bar 0. So I have dx bar 1 by dx bar 0 plus v divided by divided by 1 plus v dx bar 1 by dx bar 0. And so this is equal to v bar plus v divided by 1 plus v bar. Okay. So this tells you how velocity of a particle transforms from one system to another. Now there is a check which we can do. Suppose v bar equal to c. Okay, so no, I will not. Suppose, okay, put it in different color. Suppose particle is traveling at speed of light, suppose a massive particle, in k bar frame. This implies that v bar equal to 1 because we have taken c equal to 1. Okay. And this implies v is equal to 1 plus capital V by 1 plus v, which is equal to 1, same as speed of light. So this shows what we started with for Lorentz transformation. If a particle is traveling at the speed of light in one frame, it is traveling at the speed of light at the other frame also. It is to do, this is, I think, this is just a re-emphasis of the fact that the speed of light is invariant when you go from one inertial frame to another. Is it clear?
Yes.
Yes.
Okay. So now, so this is to do with velocities. Now let us get slightly more greedy. Okay. And let me consider now a particle. Okay. Now consider a particle. Video. A particle moving in any arbitrary direction. Direction of the velocity of the frame is still along x or x bar axis. So is the system is, so now I am saying that a particle is, so here I was saying that the velocity is, so here what I did was the velocity was parallel to the x axis. Okay, because I was taking y equal to y bar, x equal to x bar, and that was constant. Now I am going to talk about a particle which is traveling in an arbitrary direction. And then what we can say is, so what will happen is, so let us see this. So we already, so let me just rewrite those relations. I have x1 equal to x bar 1 plus v x bar 0 by 1 plus, what was it? Okay, so x bar equal to x1 equal to Huh. Sorry, not 1 plus.
Square root of.
Yeah. 1 minus v square. And I had x0 is equal to x bar 0 plus v x bar 1 by square root of 1 minus v square. However, I had y1 equal to y bar 1 and z prime equal to z bar 1. This is what I had, right? So this is just the, this is just for just a transformation from one coordinate system to another. So if there is a small differential, okay, then I have, as before, dx1 is equal to, as I just done, dx1 bar plus v dx0 bar divided by 1 minus v square. dx0 is equal to dx bar 0 plus v dx bar 1 divided by 1 minus v square. And dx prime will be equal, dx, dy, oh, I mean, I'm sorry, I should x. No, wait.
X2?
Yeah, I'm sorry. Yeah, okay. So I have dx2 is equal to dx bar 2. dx3 is equal to dx bar 3. See, what is being said is, there are 2 points. The particle is going from one point to another in time dt. This just says that the initial point, how it transforms, the final point, how it transforms. Since it is parallel to the x-axis, the change in the y coordinate, both in final and well as initial position, is the same, y and z coordinate. That's why this happens. However, now I want to do one thing. I want to calculate velocity. In the situation where it is not parallel to x-axis, calculate velocity. Now, although dx2 and dx3 are the same, in velocity I will divide by dx0. And that dx0 transforms. And that is why the velocity will transform. And so I have dx as, okay, yeah. So I have dx1 by dx0. This is as before. dx bar 1 plus v dx bar 0 divided by dx bar 0 plus v dx bar 1. Now this is equal to, since it is moving in an arbitrary direction, this will be equal to vx plus v divided by 1 plus v into vx. Are you clear with this?
Yeah.
Okay, because now Vx is equal to dx1 by, or I will call it this way. For uniformity of notation, I will just call it as V1. So V1 is equal to dx1 by dx0 and no, this should be bar. And this is equal to V1. So V1 is equal to, and V bar 1 is equal to dx bar 1 by dx bar 0. Now I calculate V2. V2 is equal to dx2 by dx0, which is equal to, this is same as dx bar 2, because it's same as this one. Okay? But the denominator changes. The denominator is, where is the dx0? Yeah. It is dx bar 0 plus v dx bar 1 multiplied now by 1 minus v square because coming in the denominator. Now if I divide it by this one dx2, this is equal to v bar 1 square root of 1 minus v square divided by 1 minus v1 plus v bar 1, which is wrong, 2. Because dx2 by, and this is also, sorry, wait, I'm wrong. This is 1. Okay. So the V2, now you see here what V2, V1 is coming. Why is it coming? Because the x-axis is special. It is the direction in which the other frame is moving. That is why this is special. Similarly, if I calculate V3, this will be equal to V bar 3 square root of 1 minus V square by 1 plus V bar 1. Just calculate this, and this is what it is. Let me just check if this is correct. Yeah. Is this clear?
Yeah.
Okay, so this is how the velocity transforms. And armed with this, I can now go one step further and ask, how do angles transform? Now, this which I'm doing is not for purely an academic exercise. This is one of the most important things in high energy astrophysics, and I'll just come to it, this particular transformation. So now, suppose I have the particle, no, suppose, consider now transformation of angles. Suppose I have suppose I have what was it? Consider particle moving in the XY plane. Now, I can always do this. I'll tell you why. Because suppose I have a particle which is moving. Now, so as before, the frame I have chosen is still something which will this is the one. This is K bar and this is K. The movement of K bar and K bar is along the x-axis. Now, if I had a particle which is traveling in the x direction, then with no loss of generality, I can say that the y components don't change with time in any frame. So it means that y bar final is equal to y bar initial, y final is equal to y initial, z bar final is equal to z initial, and z bar final is equal to z bar initial, z final is equal to z initial. With I can always choose system. Now I am saying that the particle is going in an arbitrary direction. If a particle is going in an arbitrary direction, in general, I would say that both z and y coordinates are changing, right? Is it okay?
Yeah, it is.
Okay. But I can do one thing. The direction of velocity gives me a particular direction. I can always choose, I can always rotate my coordinate system about the x-axis in such a way that the movement of the particle is confined to the xy plane. Right?
Yeah.
Okay. And okay, so at that instant, it is the xy plane. So I can with no loss of generality, I can consider only the XY plane, and this will not be any special situation. I can always convert any situation into this. Instantaneously, I can have, so particle could be moving in an arbitrary trajectory, but at a particular instant, I draw the tangent to the trajectory. That will be the instantaneous velocity. I rotate my coordinate system about the x-axis in such a way that this instantaneous velocity of the particle lies on the XY plane. Is it clear? Okay, fine. So now I consider such a geometry, and hence now I can say that if suppose v is the speed of particle, mind it, I have said speed, not velocity, in k frame, and v bar speed of particle in k bar frame, then the v1 component is equal to v cos theta. Theta is the angle made with the x-axis or theta bar, depending on which frame I am in. Similarly, I have v2 is equal to v sin theta in the k frame. In the k bar frame, I have similarly v1 bar is equal to v bar, because the speed will be different, into cos theta bar. It is some other angle. And v2 bar is equal to v bar sin theta bar. Okay? And what we need to now do is to find a relationship. And what we need to do is to, I just admitted. Hello? And what we need to do is to find a relationship between theta in barred and unbarred system. Okay? And how do we do it? Okay. So now let me divide these two. I will have V2 by V1 is equal to tan theta, because V will cancel out. Similarly, V bar 2 by V bar 1 is equal to tan theta bar. Okay? I know the transformation V1 bar transformation. I know V2 bar transformation. And I can use this to get theta bar transformation. So that is going to be the way we do it. Okay. And so how do we do this? Now now I will use these relationships of velocities which we just derived. Recall that, okay. V1 is equal to V bar 1 plus V by 1 plus V bar 1. And V2 is equal to V bar 2 square root of 1 minus V square by 1 plus V bar 1. Okay. And so I divide these two. So I have V bar 1. So I have V2 by V1 is equal to V bar 2 square root of 1 minus V square by 1 plus V bar 1 into 1 plus V bar 1 divided by V bar 1 plus V. And this is equal to V bar 2 square root of 1 minus V square by V plus V bar 1. Okay? And this is equal to so this is V bar 2 by what am I doing? No, sorry. This is equal to tan theta. Okay, because this is equal to tan theta. Okay, so okay, let me just note. Okay, let me just right. And now what I do is I just simplify this further. So I have tan theta is equal to V bar 2 1 minus V square by V plus V bar 1. And I divide throughout by V bar 1. So this is equal to, I don't know whether it can be given in a better way. Sin theta, cos theta. Let me see. C says V bar. Okay. So this will be equal to, let me see. If I divide, this will be tan theta bar square root of 1 minus V square by V by V1 plus 1. And this is equal to sin theta bar square root of 1 minus V square I'm doing a mistake. Okay, let me see. I'm dividing it by. So, okay, so I have P by V bar prime plus cos theta bar.
Have we forgotten the V bar one out?
We have taken out V bar 1 from denominator. And sorry, there is some missing something.
I think in the denominator it's V by V bar and not just the one.
Sorry, I mean, yeah, just a minute. So what is, where is the mistake?
Cos theta bar plus V by V bar, not V bar 1. In the denominator. It's like multiplying cos theta bar throughout numerator and denominator.
No, I have taken V1 bar out now and made it into tan theta bar here.
Yeah, but in the next step, when you tried simplifying in terms of sign,
yes,
put the cos theta bar in the numerator and into the denominator.
Oh yeah, okay.
So that cancels one cos theta bar, and you get only V by V bar, not V bar 1.
No, wait a minute. So this is okay. No, I don't know if I'm missing something. Just a minute. Till here it is okay?
Yeah.
Okay. And now I will have sine theta bar square root of 1 minus v square by cos theta bar into v by v bar plus 1, right?
Yeah.
To v plus v bar.
V bar 1, right? In the bracket. V by V bar 1 plus 1.
Just a minute. V bar 1. Yeah, that's correct.
Yeah.
But I'm not happy with this. Why am I not happy with this? This is tan theta bar is v2 bar by this one. This is v square. Actually, in the Landau-Lifshitz thing, there is a mistake in this formula, so I have just worked it out. So v bar. Okay, fine. That's correct. Yeah, this is okay. Okay, so no, just a minute. So this is this one. So I have sine theta bar square root of 1 minus v square into v bar 1 by v plus v bar 1 cos theta bar. Now this I am having a bit of a problem. Because why is cos theta not multiplying? Why is it multiplying this? Some error I have done. V1 tan theta. No, I think it's okay. I think it is okay. Let me just compare with Landau-Lifshitz. I know there is one error in the Landau-Lifshitz thing. No, I'm... And can you just check this anyway? Because, see, one thing is Landau-Lifshitz gives this V as different. It gives the V as the V of the particle, which is wrong. But I'm not sure about this thing. Suppose V equals... Okay, let us check with a special case. V prime is 0. No. So if capital V is 0, if capital V is 0, then both the things should be equal. Yeah. Capital V is 0, it matches. And here if capital V is 0, also it matches. Now, if theta prime is 90 degrees, no, that doesn't work. This is -1, then... Now, if theta... Okay, so if suppose my theta is equal to pi, that is going in the backward direction. That is, the particle is moving in this direction, suppose. Then theta is pi, then tan theta equal to 0. And if you substitute it over here also, it is 0, that also matches. I'm a bit, I don't know whether it's an error in Landau or this is okay. Okay, so let me see. This is tan theta is equal to V2 by V1 and V2 bar, no, V2 by V1. V2 is equal to V2 bar 1 minus V square by 1 plus V1 bar V. This is okay. And then I have divided by V1 which is V1, this one, this one. This is also fine. Which is here. And that gives me V bar 2, 1 minus V square by V plus V bar 1. And if I take, okay, so V2 bar will be equal to V1 bar tan theta. Okay, so let me just do it quickly, one more thing, and then we will know what's. So I will have tan theta is equal to V bar 2, 1 minus V square by V plus V bar 1. This is equal to V bar 1 tan theta bar square root of 1 minus V square by definition of V2 bar. This plus V1 bar. And then this will be equal to V1 bar sin theta bar 1 minus V square by cos theta bar V plus V prime 1. Yeah, so I think this, okay, so this is in Landau-Lifshitz fourth revised edition. I think there is an error in equation 5.4.
Yeah, they have missed the cos theta component.
No, they have not. See, they should have multiplied cos theta by
On
4.
both, yeah.
They just multiplied by V bar. I think
prime.
that's good. Okay.
Yeah.
Anyway, you just check this independently. Okay. Now, there is an interesting thing here. What is that? It is V2 relation. Okay. Suppose, and okay, so one of the interesting implications for this is what we call aberration of light. Okay, and what is this? It says that if a photon is moving in, okay, so let's, okay. So a particle is moving with respect to the observer. Okay. A photon is emitted in a direction which makes an angle theta with direction of motion. In particle frame. So there is a particle, it has emitted a photon, and the particle is itself moving in this direction. And this is theta. Okay. What is the angle which the observer will measure? Is the problem clear?
Yes.
Okay. Now, what is the difference between this and what we did here? This is just a special case of the first one. So in this case, if we compare with the previous discussion, the V is equal to V bar equal to C, just speed of light, because it's the particle which is now traveling is photon. Correct?
Yeah.
Okay. Hey, what about others?
Yeah.
Yes.
Okay. And so what we will do is we substitute V equal to V bar equal to C, which is equal to 1 for us. And so I have tan theta is equal to C times sin theta bar 1 minus V square. This is still 1 minus V square because capital V is the capital V is the speed of the frame, not of the particle. This divided by cos theta bar V plus C. I'm getting very worried about this factor. I will check this. Anyway, so this is the thing. So what it says is, yeah. So it tells you and I'm still a bit worried about this. No, I think it is wrong. I think there is some mistake in that theta. This one. Or this is V1 bar sin theta bar 1 minus V square by V bar. Sorry, V bar 1 cos theta bar plus capital V. I don't know. Okay, I don't know. We have to check. Anyway, so fine. So when I do this, this is equal to tan theta bar square root of 1 minus V square by V plus C. And so what happens is when V equal to 0, so it is just V plus 1. When V equal to 0, tan theta equal to tan theta bar, which is expected, right? Now, when when V is not 0, then tan theta is less than tan theta bar. Okay? It means that in unprimed frame, the angle, the direction in which the photon propagates has changed. In particular, if so in particular, what happens is, if suppose I have a particle which is actually emitting light in this direction in its rest frame, but moving in this direction, and an observer is seeing it, this angle which the observer sees will become narrower. Okay? So or in other words, if suppose you have light which is isotropically going in all directions, then with respect to the observer, this light will be more in this direction of the observer and less in this direction, because this angle is now smaller than pi. Do you actually appreciate this point?
This is
Could you
relativistic
repeat that?
beaming, isn't it?
Yeah, it is. That's what I'm saying. I'm getting to relativistic beaming in this way.
Mm-hmm.
Can you repeat that? I'm kind of lost.
So, So basically, what it says is, okay, so let us put it this way. Suppose I have a particle which is beaming light in this direction, in this frame, like in the torch which is going this. And the particle is also moving this one. And this is an angle theta in the particle's frame. And I have an observer here. Now, what is happening? This angle is going to become smaller because of for this observer. This is the unprimed frame. This is the moving frame. This is the k-bar frame. So this theta is going to become smaller. So the energy which was the number of photons which were in this cone have now got into a narrower cone.
It appears to have gotten into it.
No, it is. As the observer sees, it is narrower cone.
Oh, yeah, that's what I'm saying. In the observer's frame, it's in a
Yeah. So what it says is something very interesting. It means that if suppose you have an astrophysical object which is rushing towards you at a high speed, or for example, there are these things called jets, like you have quasars.
Yeah.
And they have jets which are there. Now, if the jet is going in the observers towards the observer, then this light from the jet looks more intense than it is in its own frame. Because all the photons which were in a broad cone in the jet's frame has confined itself to a very narrow cone in the observer's frame. Is that all right?
Yeah.
Yes.
Okay, so what I will do is, maybe I will stop here. What I will do is, I will check this formula again and then actually calculate, because here it is just the theta, so I have to calculate delta theta, how delta theta transforms.
I have a
All right.
question. So if you were to detect those photons which are coming from, or which appear to come from a very narrower cone,
Huh?
how would we like? So how would we measure what the actual uh, beam width is?
No. Okay, I will tell you how do you do that. Okay, it's very interesting. You see, there is this thing called synchrotron radiation. In which you have a magnetic field and your charged particle going around at a high speed. Okay? Now, suppose an observer is over here. Suppose the particle is going at a very high speed. The total energy has to remain conserved. So when the particle is here, in the frame of the particle, all the photons are being emitted isotropically. But in the observer's frame, it is in a narrow cone over here, so the observer does not see it. It's all very hardly any energy is coming in this direction. The energy is completely confined in this direction. As the particle comes here, it is in this direction. And when this particle comes here, it is in this direction. But now what happens when it is here, the beam is there, but when it's here, the beam has gone, which means the observer seems to see the beam for a very short time when it is actually moving almost in his direction, when the thing is going around.
Okay, so the rest of the time it's invisible. That's cool.
So rest of the time it is not visible. So what happens is, because of this, if suppose it was moving in a non-relativistic way, this observer would have seen this as a low intensity all the time. Because of this, the observer primarily sees it only when it is moving almost in that direction, but all that energy is now compact into that cone. So he sees a very high energy pulse for a very short time.
Okay.
Okay?
Yeah.
I mean, so it is something like if there is a circle and you have a particle going in a circle, and I've actually kept a torch. If an observer is here, I'm not going to see the torch. I will see the torch only when it is facing the observer. But I will see it only till this observer is in this angle. Otherwise, I will not see it. So this beaming which is there by the torch here happens because of relativistic effect. Is that okay? Hello?
Yes.
Yeah, yes.
Yes, yes.
Okay, okay. So I will continue with this next time, next Thursday. Yeah, what is next Thursday? Today is what? 18th. 18th plus 7, 25. Okay, fine. Fine. So 23rd, I will continue the track 1. So is this track 1, track 2 okay for you?
Yeah.
Yeah, it's fine.
Yes. Yes.
Ariel, you're saying something?
I said yes. Yes.
Okay. Fine. So let us, yeah. Okay.
Sir, sir,
Huh?
can you share last class
Oh, I have
recording?
not done that. No, I will do both this. That is the Tuesday one, right?
Yeah.
Yeah, I will do that. I will do that by this weekend. I will do all that. This one and last one also. Yeah. And I'll also make some problems in
Okay.
here. Okay.
Okay.
Chalo. Okay. Bye. Good night.
Thank you, sir. Good
Good night,
night.
sir.
Yeah.
Bye.